Hello, good evening. I'm Suman Senapati. So I'm doing my masters in applied AI, and for my capstone project, I have selected to work upon a deep reinforcement learning agent coupled with a multi-agent framework for optimization of crude distillation unit. So my prime target, my objective in this project is to build a cognitive multi-agent physics grounded RTO for a crude distillation unit. I will first explain how in the workflow. I'll first explain how we collected the data. In this case, we don't have uh, uh a labeled data like we do for machine learning, supervised machine learning problems. Instead, what we are more focused on is getting crude assay data for building the flow sheet. The flow sheet essentially becomes the prime gymnasium uh, environment for training our deep reinforcement learning agent. So the DRL agent learns how to select the correct action based on the states, and whether the actions are uh, grounded in reality or not is decided by the flow sheet. As since the basis of the flow sheet is completely grounded in physics, because all the associated first principle equations which are required for solving a distillation column is already coupled inside the DWSIM environment. It becomes the primary candidate for building the custom gymnasium environment for training of the DRL agent. On top of that, once the DRL gets trained, once the DRL uh, figures out how to choose the right set of actions for the right states, we have built a separate multi-agent system on top of it, which decides if the selected actions are uh, if they make sense in to add a layer of explainable AI on top of this, and to cater to other requirements such as uh, for preparation of reports, for understanding corrosion in the overhead section of the distillation column, or for understanding of the process. We have built three separate AI agents, which then finally pass on their recommendations to orchestrator, which gives the final report. So, talking about the data, what we have taken here is our open crude assays available on ExxonMobil's websites. So, from there, we had selected five crude assays, namely the Azeri Light, Erha, Tapis, Apazakum, and WTI Light. These are completely different types of crude. If you talk about the API gravity, they have very different API gravities. So it's a complete spread. So you get very light sweet crude to very heavy crude as well within these five selections. So what we have done, we have gone through a thorough technical assay analysis of the crude, where we looked at all the major properties which affect my the entire process of crude distillation, not just the CDU, not just the crude distillation unit where we separate the crude into various products. Instead, we also look at presence of metals, presence of nitrogen, presence of sulfur, which ideally affect my downstream process units where uh, more complex processes are involved, like such as let's talk about an FCCU where which gets affected by high metal presence. So an FCCU will have catalyst inside the reactor region section. These catalysts tend to coke up in the reactor, and then the coke is removed in the regenerator. But then again, if too much metals, if in presence of high metal in the crude, that ends up with the vacuum gas oil and the vacuum residue, which finally again increases the bed temperatures for reactor and the regen section. So the crude selection becomes very essential, especially for when you're trying to increase your crude throughput in the refinery, and there are multiple limitations with respect to the process and with respect to the equipments. Crude selection becomes very crucial, I would say. So here we have done a thorough analysis. The analysis, the report of the analysis shows that uh, if we build a, a flow sheet for ERHA, we would have you would say a generic flow sheet. Instead, if we go for any other of the crude, it will be pretty specific. So we went ahead and we built the flow sheet around ERHA. This can be extended beyond ERHA. We can have other crudes as well. So we can build separate flow sheets, or within the same flow sheet we can build a separate stream which corresponds to other crudes. Only thing is, with the DW sim bringing in multiple pseudo components from different crudes makes the solvability of the flow sheet difficult, because again this is open source software, unlike any paid commercial softwares which make kind of life easy when you're dealing with multiple crudes in the same flow sheet. Here it becomes that tedious to build it, so we decided to make choose only one single crude and proceed. Talking about the flow sheet, so crude distillation unit typically has three different distillation columns. The first one would be the atmospheric distillation column, which essentially is fed with a heated up crude, and it separates the crude into a bottom and the top moves on to the next distillation column, the naphtha stabilizer unit, and there are three or four side draws. In this case I have taken four. So we have heavy naphtha, kero or ATF. ATF is basically jet fuel, and two separate diesel streams, and the bottom is again passed on via a furnace to heat it up and fed into a vacuum distillation unit which runs at nearly absolute vacuum. So the vacuum distillation unit again further uh, fractionates the bottom from the atmospheric distillation unit into multiple distillates. This and finally the SR, the short residue or vacuum residue left out in vacuum distillation unit, is ideally the bottom. Everything else can be called a distillate, and there we have segregations. We have light distillates, middle distillates, and heavy distillates. So these have different pricing based on how they are processed and finally what products are made out of it in the market. So we have put a separate dictionary for that. Later on I'll discuss that, and the pricing is decided based on typical market price of the final product. Here we have this essentially works as a process digital twin for a crude distillation unit. So any changes, let's say if I want to increase the reflux rate, or if I want to draw more naphtha to gain more value, that experimentation can be done on the flow sheet. I can see what effect it would lead to if I increase my naphtha and reduce my diesel, or vice versa. If I increase both, how it will affect the temperature profile in the column. If finally it's if the solver is able to handle that or not, that is also very important. We could end up with uh, numbers which are not a proper solution to the problem. So that is why we chose an open source process simulation software to build the environment, so that whatever numbers my later on my reinforcement learning model ends up with becomes physics grounded. First of all, see, nothing, any number which my deep RL decides, the optimizer decides, should be usable in an actual plant. Otherwise this has no value. If it's just some number which is not, I am not able to push it to my actual plan, then it becomes garbage. So it's very very important that we have a proper environment for the agent to learn how to behave, how to increase crucial streams or ratios, for that matter, reflux ratios, or let's say the reboiling, how to increase the reboiling. These kind of things are very crucial in this. Okay, moving on to the RL agent architecture. So how it works is, first I'll just let me clear up how my application works. So the RL agent would be communicating with the DWSync environment. It will test different actions against different states, and DWSIM will either fail in converging, or if it converges, it will give back a certain set of solution which contains all the streams, all the flow rates, all the temperature profiles, and finally my reward function will decide whether the rewards are increasing or not. The rewards are again based on multiple factors. One is the product profile. If my high value products are increasing and low value products are decreasing, then I get a thumbs up, I get a higher reward. At the same time, the column should not be pushed to the extent where it's about to flood or about to weep, into a process anomaly section. That is also looked at in the reward section. So these two major factors are looked at, and of course the consumption of utilities. The utility consumption should go down. So my overall economic factor is present, and overall my process uh, stabilization factor is also part of my reward section. So if the rewards are going up, the RL agent will keep pushing the plan towards a more optimized value. So whenever, so it will get stopped where, so the episode will crash, the episode will end whenever the solver crashes, or I'm getting a solution which is reducing my reward. So in such a case, the episode will end. So in here, what we have done is, we have based on the use case, since this is like driving a car, not, we didn't choose a deep queue network or some solution like that. Instead, this requires more subtle control. That's why we chose these three major algorithms for trading. So what is my rationale behind choosing these? The first one, soft actor critic, basically what it will do, uh, so essentially they all work in the same principle. They will be looking at, they run on very three different RL philosophies, right? So their major goal is to find a robust solution which works across different plant conditions. The first one, the soft actor critic, is more uh, uh, okay. So for soft actor critic, what the justification for selection of this is that, first of all, it's an off policy method. That meaning basically it will learn from its past experiences as it propagates through different circumstances, build across uh, the training cycle. It will learn what has already happened. So every time it runs an episode, the results and the actions, the choices are stored in a buffer. So in the next episode, it will already know what all has happened. So what to do, what not to do. This kind of an idea is built in an off policy RL algorithm like soft actor critic. So it will have that idea. It also uses something called maximum entropy. So this will basically reward the agent for finding new sets of parameters, new sets of uh, actions, while seeking the actual good, a higher reward. So every time it tests a new set of actions, instead of doing the same thing over and over again, it will be rewarded more. So this kind of a algorithm has a tendency to search across a complete vector of actions and understand which works best, If it doesn't work best, also it will still store the result in a buffer. We set a buffer size as a hyperparameter, and it learns during the process itself. So that goes for uh, soft data critic. Similarly, when we chose twin delayed DDPG, what works is this has a very good tendency of stability. So it uses two different critics to double check the work. That's why twin delayed comes into the picture, and it delays the updates to ensure that learning just doesn't become jittery. So this works in a pretty different principle. So but there's a challenge here. It sometimes has a problem called overestimation bias, where they think a certain setting or a certain action is much better than it actually is, leading to erratic behavior. That is one challenge with twin DDPG. This is exactly where my third algorithm comes in, which works like a reliable fallback policy for all three architectures. So here, it's actually very easy to tune this kind of algorithm, where the third one is proximal policy optimization. It's pretty straightforward. It's an on policy algorithm, where this is exactly opposite to soft attack critic. So PPO has a tendency of improving the current strategy directly. So what it will do is it will use a more sort of a clipped objective function, which will prevent the agent from making a change which is so large that it destroys the performance it has already gained. So let's say it's going in a certain direction, it's improving every step. So once it does, it becomes more privy to the change, and it takes smaller steps, so that it does not lead to an episode crash in the process. So these three worked in very three different principles. Why did I use all three of them? Ideally, I want uh, an architecture which will always push all three to learn. So now, once my agent is trained during the inference stage, I have nothing to worry about. Even though the training is a really long process, here I've only trained it for 500 steps, but ideally this should be trained for at least 100,000 or 200,000 steps. Now I don't have the hardware for that, sadly, since I'm doing it on my notebook PC. But of course, when you're doing it on a high grade server, this training can be handled without much uh, headache. So since this is just for academic purpose, I have only trained for 500 steps. We'll talk about the hyperparameters chosen next. Uh, So how the training works, how in fact the whole architecture works. So the DWSIM flow sheet, like I was telling earlier, works as a custom gymnasium environment. Uh, Scholars who have already worked with reinforcement learning know that most of my RL agents work within either custom gymnasium environment or environments which are already there in the the standard gymnasium library of Python. Of course, you can build more in Unity in other places. So here in our case, what we have done is we focused on building a flow sheet based gymnasium environment, and DWSIM luckily comes with a automation bridge which allows you to communicate with different parts of the flow sheet externally through Python scripts. So we have built a Python bridge which we are using for both our RL agent and for our multi-agent AI framework. So it communicates with the flow sheet. It can read, it can write, it can do anything inside the flow sheet. I can increase the tolerance, I can change the flow rates, I can change any parameter. So this is a standard uh, framework already built upon DWSIM, and it's well documented on its website as well. So our life gets easy there. So we just built a wrapper around DWSIM, making it a custom gymnasium environment. And during the training phase, our RL agents, multiple uh, agents, were communicating with DWSIM where they were testing out how well set of actions based on the states are working. And later on, when the multi-agent framework came based on the solutions found, the multi-agent framework was running the individual AI agents, and then finally an orchestrator was uh, summarizing the outputs from each agent through a chain of thought process. So these are the hyperparameters. You can see the total time steps are only 500. I tried with somewhere close to 50,000, but it took me a half a day, and then I realized that this is not going to work, at least on my laptop. So I brought it down to 500. Even then, this training took me around 4 hours on my laptop. This becomes tad tedious because the environment again is external. So every time, for every step, it's connecting with GWSIM and running the actions, and the simulation runs. The simulation itself takes some time for convergence. So the training becomes that tedious. Unlike your regular gymnasium based RL agents, which run pretty quickly compared to this. Anybody who has worked with reinforcement learning would know that the gymnasium environment is pretty fast. Generally, we tend to train for 1 million steps, and it barely takes 2-3 hours. Here, for only 500 steps for each of these, so 503, so only 1500 steps were used, and still it took me around 5 hours to run the entire notebook. So the max episode step decides a reset parameter for the episode, right? So if it doesn't crash up to 50 episodes only, it's looked at. And we have other things are pretty straightforward. The learning starts after 100 time steps only. So last 400 time steps are where it learns. Batch size is pretty common for any neural network. We exactly know how a batch size works. It decides how many rows would be present in each batch. Learning rate is used for back propagation. So uh, here we have concept of discount factor, buffer size, and we have introduced something called action warm up. This is not very common. What exactly happens is, since DWSIM again has its own solver, and there's a chance that it will crash if we pass on very big actions. So the action, what should I say? The action tensor values are passed on not as the values directly. Instead, the action sizes are controlled. Initially, the action sizes are very small. We only take 5% of the action, and then slowly we move. As we move ahead in the time steps, we slowly increase the size of the action. So, also, what we have done here is to ensure that it doesn't crash very frequently. We have made the solver, DWSIM solver tolerance adaptive. So the RL agent also can control the solver. So what happens is, it starts with a higher number solver tolerance, maybe 0.1, and then it sees if we can push it below. The smaller it gets, the better it is, right? But it does not go beyond 1. But of course, so it keeps pushing the tolerance lower and keeps checking if this is able to handle it. For the curriculum, we chose a full difficulty curriculum, so that the solutions are fully grounded in physics. Same thing which I was explaining earlier. You can see how the action magnitude from the initial step 1 is only 8%, and how it has increased at step 25 to 73%. At step 50, it has gone up to 100%. And we have clamped the actions to certain values, because again, the action should make sense. If I, let's say, have a heavy naphtha flow of 10 meter cube, or let's say 15 meter cube, the action cannot be, the next step will be 500 meter cube. So the actions also have to be grounded in physics. Now, talking about the multi-agent architecture, as I was earlier explaining, what we have done is we have used open router API for testing. Again, here the ideal case would be to run a small SLM or an LLM locally on certain server using the API, making API calls for inference, and using the same for the training process. Since we could not do that for academic process, what we have done is we have used an open router API. which comes free, and using that we have built three separate agents. Each agent runs as in chain of thought. So it the output of each run is fed as a thought process to itself, and it thinks several times over, finally deciding on a proper uh, response. So now we have three separate agents. Each agent would be giving an output, and finally the final output will be going through an orchestrator. The orchestrator will finally give a solution. I have not discussed the result of the multi-agent architecture here. It's there in the notebook. Basically, it provides a report. So the report is mainly talking about how the process can be improved further if the RL agent is going in the right direction. The daily report developer creates an end-to-end unit report. The corrosion expert talks about overhead corrosion. Now, in this case, we had one difficulty, that is, since we are not showing any steam in the column, ideally corrosion should not happen, because the HCl vapors which are produced during hydrolysis of calcium chloride, magnesium chloride salts present in the crude finally require condensation of the steam which is introduced at the bottom of the column, and for stream steeping at the overhead section for the corrosion to occur. Now that is not the case here. So ideally the corrosion expert can only look at dew point. Okay, talking about the results, we tested all three algorithms, and uh, PPO, the proximal policy algorithm, gave the highest, the best reward, the best average reward across 100 episodes. Again, like I had discussed earlier, is the safest option to use. So we have three different uses for three different algorithms. We could actually go with all three and build a wrapper around it. Where if the unit is not very stable, we could choose PPO. And during stable cases, we could choose soft critic or twin delayed DDPG. So that is to be decided. Similarly, you can see the results through a plot. You can see the highest average reward is seen in case of PPO. Again, these numbers might change if we actually run the training for much longer. We only could train it for 5 minutes. I mean 500 steps. So I think that's it from my side. I hope this uh, was an informational presentation. I could cover all the aspects here. My sincerest gratitude to our guide, Professor Haisaf Chokshi. He has guided me across these all 7 weeks. Thank you, sir.